Thanks, David. I'd like to introduce Daniel from Pythian. He's a Windows SRE, which is awesome. But today he wears many hats, and he's going to talk about multicast of networking.
Thank you. All right, good morning. So, thank you. My name is Daniel Emord. Like you said, I'm a lead site reliability consultant at Pythian, and we've got a pretty wide range of clients with different technologies, different processes, and sometimes we get some pretty interesting requests, and this is one of the ones that I wanted to talk about today. So this particular client had all their services running on-prem. It was all Windows-based. It was a, I guess, legacy app in this context. It might be a little harsh on them, but it's something that had been around for a while. So this was one of the apps that they did want to move to AWS, and they had some issues because this app utilized Multicast to synchronize the state, basically transactional updates between the different nodes. And they found out pretty quickly that Multicast is not natively supported on AWS, or pretty much any of the major cloud vendors. Azure, at least as of the time of when we were looking at this, I know they were talking about it, but I don't think they've gotten there yet. So that led them to asking us, hey, how can we get this fixed? So before we go into some of the solutions, look at what Multicast actually does under the hood. Basically, it's a mechanism for sending a single packet once from the source and having it delivered to multiple destinations. So instead of setting up a unicast stream to server ABCD and sending 4 packets, you just send 1 packet once, and anyone who wants to receive it, who wants to consume this data, can. You just need to request to receive this data using IGMP. There's version 1.2.3, depending on the functionality that you need. But basically, you have to request to get this data. So it's an efficient way of getting a lot of data to multiple recipients pretty quickly. So some solutions that we looked at for getting this application, this particular app, into AWS, one would have been redesign the actual application. Can we leverage some sort of queuing mechanism, something a little bit more modern, more, I guess, native to AWS or to cloud platforms, something that is a little bit more flexible in this regard. But surprise, surprise, they didn't really have time to do that, and it was, come on, get it done. Crap. All right. So we started looking at OpenVPN and doing it more of a mesh, but they didn't really have good tooling to make this a little bit more, I guess, easy to deploy and manage. They wanted to be able to just have a node completely crap itself, whether it be an AZ went down or the node itself went bad. They want to just be able to redeploy it at a drop of the hat, so that wasn't really going to work for them. So then we looked at end-to-end, which after my talk, I know, I think it's Fran is after me. He actually had end-to-end, didn't work out for him. So I'm curious to see what he ran up against. But we found that it worked pretty well. We turned off a few features that we didn't need, and it's been running in production for 8 months now. So with that, I want to talk a little bit about the end-to-end architecture. And, all right, that actually came through all right. So within end-to-end, you've got the supernode, and this is basically what handles all the registrations. It's the brains behind the operations. And this is what all the edge clients, this is the forwarders, they will all register against the supernode, and then the supernode will establish or tell you which clients you need to talk to if you're trying to reach IP address XYZ or whatever. It also handles the multicast and the broadcast traffic. I'll get into that a little bit more in the future, or later on here. There's also capability for encryption and compression. We already had a direct connect link to AWS right from their on-prem, and they already had a backup link through IPsec across the internet, so we didn't really need to worry about that. And they had some pretty good bandwidth, so this was a very low bandwidth app. Didn't really need to look into that. So one of the things that we looked at, or was a requirement for them, was high availability on the application, or on this multicast routing, because they had processes built into the app so that if a single packet was dropped or there was a network glitch, the service restarted, they didn't need, it wasn't catastrophic to them. They could either request, packets 2, 3, 4 out of a sequence to be retransmitted, or they could pull an initial state sync out of a SQL database, but this wasn't fast, it wasn't efficient for them, so they wanted to have some semblance of reliability. They didn't want it to be relying on a SQL pull every 5 minutes in the middle of the night when one of these nodes went down. So we had to have the gateway routing nodes to be highly available within the environment. The way that we did it was using CoroSync and Pacemaker, handling the actual synchronization or the service availability of the routing portion on Linux nodes on-prem. And we weren't concerned with duplicate packets because, again, within the application, they had the capability of just filtering it out. So, all right, big whoop-de-doo if we have 2 nodes routing at the same time for a split brain kind of scenario. Wasn't the end of the world. So that's something to keep in mind as you're designing your network if you decide to go this route. But for this, it wasn't really an issue. The on-prem routers, because you're setting up a new subnet as a VPN within end-to-end on AWS or even on-prem if you want it as well, the on-prem routers need to know how to get to this end-to-end network. So you need to make sure you have a static route or however you want to assign it to point to either a single gateway router or a floating IP. As you can see here, we had a VIP, just again also being managed by CoroSync and Pacemaker. And finally, depending on your topology and the devices you have in play, you might need to enable IGMP snooping or multicast routing on the devices. In this case, they had Juniper gear in place. They needed to make sure everything was configured appropriately. And there were some hiccups all along the way there. I think they had some security issues. We worked with the networking team. We didn't have access to that, unfortunately, but they got it worked out and it's working now. So for this on-premise gateway, again, this is to handle getting the multicast packets to and from on-prem to the nodes in AWS, or more accurately, to the nodes within the end-to-end mesh. We needed that automatic failover, and that was, again, was handled with CoroSync and Pacemaker. It also was responsible, in this case, for handling that supernode service. That was also just a standard Linux service running under CoroSync Pacemaker, and wasn't the end of the world if it was in a split brain scenario, because only one's going to get it. And additionally, we needed to handle the multicast routing on Linux. There's a few different ways that you can attack it. Because this was a pretty static config for them, we always knew that 239.0.0.1 through .9 was going to be routed across. It was always going to come to and from these 2 interfaces. We just went with the SMC route. It's a pretty standard, it's an interface or a route coming in from interface A, you want it to go to interface B, done. There's also PIMD and MRouteD. These will rely more on IGMP to handle the determination of where they should forward packets. So if they see membership requests for 239.0.0.1 and E0, they know that anything coming in on any of the other interfaces should go out that. So there are some things that we needed to change within the edge client itself to make it a little bit more, I guess, easy to leverage within this solution. First, we needed to have the static routes on the Windows nodes in AWS. They needed to know that if you wanted to hit the multicast device, they shouldn't go out the AWS instance's default interface. They need to go out this end-to-end virtual interface. So in order to do that, the interface needs to be online first. So there's a service wrapper that was on SourceForge that would handle bringing the edge interface up, handling the connection, the configuration. So we had to make some tweaks to that to make sure the interface was up, add the routes, and just ensure the health of it throughout the entire process of managing the interface. We also found that DHCP was a little bit flaky on end-to-end, and instead of just trying to really dig into it because we didn't really have enough time to, we just said, screw it, we'll just use a static mapping of, all right, your hostname A, you're going to get IPB, and just having that on a web server. Again, we just threw that on that HA pair and worked fine. Just pull that down, cache it locally, and get updates whenever needed, which didn't happen very often. We also needed to make sure we had shorter timeouts because the HA solution for the supernode was not syncing the session state between the 2 different nodes. So if supernode A goes down, supernode B takes a service up, but it didn't know about all the different edge clients. The default was to register, I believe, every 20 minutes on the edge client, which would have been a pretty significant downtime. and that wouldn't have worked for them. So we just tweaked the headers on there, recompiled, and everything was good. So shorter timeouts on that, shorter registration intervals, and worked pretty well. Those edge timeouts can be a double-edged sword because it is responsible for maintaining that session state on the supernode. If you do lose that supernode and there is a unicast stream between nodes A and B, as long as that stream is alive, that the edge timeout won't really come into play. But as soon as that traffic stops, then that timeout will kick in, it'll kill the tunnel, and you have to make sure you have the supernode available in order to get that communication going again. The other thing that's a pretty big note here is the supernode handles the multicast and the broadcast traffic. So it's not as efficient as an on-premise multicast solution where it's single packet, multiple receivers. It's a single packet goes to the supernode, and the supernode will send it out to the rest of the recipients. So it is a unicast stream to each one of these. So if you have something that is very high bandwidth, this might not be the best solution. Again, this was a low bandwidth solution for them, so it worked fine. As long as you design it, you understand how much bandwidth you're going to be pushing, how many clients are going to be receiving this data, it should be fine. For those of you who might be familiar with end-to-end or do some searching later, you'll see there is a multi-supernode fork of end-to-end. So this was doing more of the app-aware HA, so you could have multiple supernodes running. The edge clients were registering to all these supernodes, but we found that was a little inconsistent. Didn't get really good failover behavior out of it, so we decided to just suck it up, and the app can handle the intermittent failures, so whatever, it's fine. And okay, I guess that was it. So all the changes that we made, some of the example configs are up on our Pythian GitHub. And with that, any questions? Mm-hmm.
It might be that this was just specific to your client, but
Cue the elevator music.
So it might be specific to your client, but for someone without a networking background, can you say why you needed multicast, roughly?
So in this instance, it was specific to the client. That was what they had on their application. They couldn't change it in time in order to move it up to AWS. So we just had to stick with it. Ideally, we would have moved away from it in this case, but there are a lot of use cases for multicast. A lot of it's right now more tuned, I guess not more tuned, but there are a lot of instances where it's utilized for clustering, for just getting some of the HA, like OSPF, or not OSPF, well actually OSPF does use it too. HSRP, that kind of stuff, we'll leverage it. But there are some deployment type solutions like Windows Deployment Services or SECM. If you have, say, 100 new desktops that you're deploying, you can just say, okay, everyone, let's go ahead and get this imaged out, set them all up, pixie boot, and send out that one image once from the deployment server. All the recipients receive it, but that's not something you're probably going to be doing in AWS.
Yeah, cool. Thanks.
Mm-hmm. Excuse me?
IPTV is like
Right, IPTV. I think someone was talking about the hotel elevator music was using multicast, and they were actually able to sniff on it, and there was some interesting possibilities there. But yeah, we won't go into that too much here. But yeah, IPTV. There's a lot of audio and video based applications for multicast. But what's that? Storage. That was new to me. So, any other questions? All right, thank you.